Welcome. This work presents an AI-based edge control approach for electric vehicle charging in low-voltage grids, with a specific focus on voltage regulation. The study was developed in the context of the ENFIELD project, addressing how AI can support smarter and greener energy systems. Low-voltage grids are becoming much more dynamic. The problem has two sides. Uncoordinated EV charging can push voltages below the acceptable lower limit, especially during evening demand peaks. At the same time, high photovoltaic production may push voltages above the upper limit around midday. So the control objective is not only to charge vehicles, but to charge them at the right time and at the right nodes. The proposed method uses reinforcement learning, with proximal policy optimization as the main control agent. PPO learns by interacting with a simulated low-voltage grid and by receiving penalties when voltage limits are violated or when EV charging requirements are not fulfilled. After each action, a power flow calculation updates the actual voltage state of the grid. The agent does not act blindly. It receives information about voltages, loads, photovoltaic generation, EV charging needs, and the network structure. This allows the controller to adjust charging rates in real time, rather than simply following a fixed charging schedule. In practical terms, the algorithm learns when to reduce, shift, or increase charging. A key part of the framework is the graph convolution variation module. This module gives the agent spatial awareness of the grid. Instead of treating each node independently, it embeds connectivity, neighboring nodes, and line impedances into the decision process. These plots show a stable convergence. As learning progresses, the reward improves and the voltage error decreases. After a certain number of training steps, the policy stabilizes, indicating that the PPO agent has learned a reliable charging strategy. The method was tested over a large scenario pool. Across these scenarios, the reinforcement learning controller consistently reduced voltage deviations compared with the static baseline. It also improved the total reward, which combines voltage quality and EV charging fulfillment. The main control behavior is demand shifting. When the grid is stressed by evening demand, the agent reduces or delays charging to avoid undervoltage. When photovoltaic production is high, it can move part of the charging demand towards those hours, helping absorb local generation and reduce overvoltage. The result is a more coordinated use of EV flexibility. The vehicles still receive the required energy by departure time, but charging is distributed in a grid-aware way.